Have you ever wondered how your brain processes information? Could a machine mimic this process? Welcome to the intriguing world of neural networks, a realm where the lines between human cognition and machine learning blur. Just as our brain is an intricate web of neurons interacting and transmitting information, artificial neural networks aim to replicate this complex mechanism. Imagine a world where machines operate with similar functionality to our brains, processing data, learning, evolving, and making decisions. This fascinating concept isn't a far-fetched sci-fi fantasy, but a reality of today. From predicting weather patterns to diagnosing diseases, these artificial neural networks are revolutionizing the way we understand and interact with the world around us. So, are you ready to unravel the mysteries of this technology? To dive deep into the labyrinth of artificial neurons and synapses that form these networks? Stay tuned as we delve into the fascinating world of artificial neural networks. Artificial neural networks are not as complex as they sound. They are just a model inspired by the human brain. Now, what does that mean? Well, think about how our brains work. We have billions of neurons all working together to process information, make decisions, and learn from our experiences. Similarly, an artificial neural network is a system of algorithms designed to recognize patterns. But why patterns? Because the world around us is full of them. When you see a red octagonal sign on the road, your brain instantly recognizes it as a stop sign because you've learned to associate that pattern with a particular instruction: stop. Our brains are excellent pattern recognition machines, and that's exactly what we're trying to emulate with artificial neural networks. So how does this work in practice? Let's take a simple example. Say you're using a neural network to recognize images of cats. You feed the network thousands of images, some of cats and some of not cats. The network then tries to identify patterns in the images that suggest catness. Perhaps it's the shape of the ears, the size of the eyes, or the texture of the fur. Over time, the network learns to recognize these patterns, and it gets better at identifying cats. It's not unlike a child learning to identify animals. At first, they might struggle to tell the difference between a dog and a cat. But as they see more cats and dogs, they start to pick up on the different features and can more reliably identify each animal. But remember, just like humans, neural networks aren't perfect. They can make mistakes, especially when they encounter a pattern they haven't seen before. That's why it's crucial to keep training and refining these networks, so they can continue to improve and adapt. And that's the beauty of artificial neural networks. They're not just static programs, they're dynamic, evolving systems that learn and improve over time, much like our own brains. So in essence, we are teaching machines to learn like us. To comprehend neural networks, we first need to understand neurons, the basic building blocks. Imagine a bustling city at night. Each light you see represents a neuron, a fundamental unit of a neural network. Alone, each light might seem insignificant, but together, they create a vibrant, pulsating metropolis, full of life and energy. That's the power of neurons in a neural network. So what exactly is a neuron? In the context of neural networks, a neuron is a mathematical function conceived as a model of biological neurons, the primary components of the brain. Each neuron takes in input, processes it, and passes on the output. This is similar to how biological neurons receive signals, process them, and transmit them to other neurons. Now, let's delve a bit deeper. Each neuron in a neural network receives multiple inputs. These inputs can be raw data like images, text, or sound, or they can be outputs from other neurons. Each input is given a weight, which signifies the importance of that input. The neuron then sums up the weighted inputs, adds a bias, which helps adjust the output along with the weights, and applies an activation function. The activation function is the neuron's decision maker. It decides whether the neuron should be activated or not, based on the input it receives. It's like the switch that turns our city light on or off. Common activation functions include the sigmoid function, the hyperbolic tangent function, and the ReLU, rectified linear unit function. Each neuron, with its weights, bias, and activation function, contributes to the overall output of the neural network. And just like a city where each light plays a part in the overall illumination, each neuron in a neural network contributes to the final decision or prediction. Just like the human brain, a neural network's power comes from the multitude of these neurons working together. And that's the beauty of it. From a multitude of simple units doing simple computations, emerges a complex, powerful system capable of learning, recognizing patterns, and making decisions. A neural network structure is what gives it the ability to learn and adapt. This statement, in essence, sums up the crux of this fascinating field. But what does this structure look like? Let's delve in. The structure of a neural network is somewhat akin to a multi-layered sandwich. It consists of an input layer, one or more hidden layers, and an output layer. Each layer is made up of numerous nodes or neurons which are interconnected. You can think of the input layer as the front door of a grand mansion. This is where the network receives all its information or data. Each node in this layer corresponds to a single feature in the data set. The hidden layers, they're like the mansion's many rooms. Here, computations take place. They use weights, which are just numerical values, and a bias, another number, to transform the data received from the input layer. This transformed data is then passed through an activation function, which decides if and to what extent this node will influence the final output. The output layer is the mansion's exit door. It's where the network delivers its final verdict based on the computations done in the hidden layers. The number of nodes here corresponds to the number of possible outcomes. But how do these layers work together? Well, it's a bit like a relay race. The input layer passes the data to the first hidden layer, which does its computations and passes the transformed data to the next layer. This continues until the final output layer is reached. This intricate interplay between layers, the computations within the nodes, and the activation functions are what allow a neural network to learn from data and make predictions or decisions. The weights and biases are continually adjusted during the learning process, enabling the network to improve its predictions over time. Just like our brains, neural networks are capable of learning and adapting, thanks to their complex structure. This structure, with its layers of neurons, interconnected and working in harmony, is the secret sauce behind the power of neural networks. The structure is what gives neural networks their unique learning ability. Remember this the next time you marvel at the capabilities of artificial intelligence. Training a neural network is like teaching a child. It involves learning, adjusting, and improving. Imagine a toddler taking their first steps. They stumble, they fall, but they get right back up and try again. Each attempt, each stumble, each fall, and each success is an opportunity to learn, to improve. This is the essence of training a neural network. Data is the teacher that guides the neural network. Much like a parent guiding a child, the network is fed a steady stream of input data. This could be anything from images and text to audio and video. The network analyzes this data, making predictions and drawing conclusions based on its current understanding of the world. However, just like a child, the network isn't perfect. It makes mistakes. It stumbles. This is where the learning really happens. The network compares its predictions with the actual results, identifying the gaps in its understanding. These gaps are the equivalent of the child's stumbles, the moments that highlight where improvement is needed. But how does a network improve? It adjusts its parameters, the weights and biases that determine how it interprets the input data. It tweaks these parameters in a way that minimizes the gap between its predictions and the actual results. This process is a bit like how a child adjusts their balance and coordination after each stumble to improve their walking. Over time, as more and more data is fed into the network and as it goes through countless rounds of adjustments, the network gets better. It learns to recognize patterns, to make more accurate predictions, and to navigate the vast landscape of its input data with ease and precision. Just like a child learning to walk, a neural network learns to perform its tasks better with each iteration. It starts with stumbles and falls, but with patience, guidance, and a lot of practice, it eventually becomes adept at its tasks, navigating the world with confidence and proficiency. Just like a child learning to walk, a neural network learns to perform its tasks better with each iteration. We've embarked on a fascinating journey through the world of artificial neural networks today. We've delved into the depths of these digital brains, understanding their structure and function, and how they mimic the human mind's complex processes. From the single neuron, the building block of these networks, we've seen how they come together to form intricate, layered structures, capable of processing and learning from vast amounts of data. We've explored the learning process, How these networks are trained using algorithms, adjusting their internal weights and biases to improve their performance with each iteration, each experience. This is the essence of machine learning. The beauty of neural networks lies in their adaptability and their potential. From recognizing patterns in data to driving autonomous vehicles to diagnosing diseases, these networks are transforming the way we live and work. Remember, neural networks are the cornerstone to many AI applications that are reshaping our world.